So I'm Koby Crammer, and this is joint work with my student Edward Moroshko. We're both from the Department of Electrical Engineering, the Technion Israel. So let me briefly start with a simpler setting of online learning with what we call the full information case. So here the algorithm maintains a model, and given that model, it receives an input, for example, a document, and it outputs a label or prediction for that document. Let's say, is it about sport or not? Is the email spam or not spam, and so on and so forth. It then receives the true label, and using that, it then computes the loss, how much, how good was the performance on that particular example. Then it can update the model given that label, and it can proceed for the next round. In particular, we consider the case where models are weight vectors indexed by time t. Inputs are also vectors, both of dimension d. We use half spaces, and we take the sum of the inner product. Labels are -1, 1, just bits. We use a 0, 1 loss for evaluation, and using that label, we can update the model and get the new weight vector for the next round. This is a very classical setting. It was studied for a few decades already. Usually, the analysis of such algorithm is in the worst case setting, and we have what we call mistake bounds. So we compare the performance of the online algorithm to a performance of some function, in this case, the weight vector or some weight vector from some class. And note that this weight vector can be chosen after seeing all the examples in retrospect, or what we call offline. And therefore, we have, or we can compare the loss function of our algorithm. Note that we have different t's because on each iteration we may modify the model. We compare it to the loss function of the individual fixed weight vector. And there is some additional loss which we called regret. And this could be because the algorithm is observing examples one at a time, while the U can be chosen in retrospect. Note that here, and this occurs in such and similar algorithm, we compare the 0, 1 loss of our algorithm and the hinge loss of the competitor. Okay. What we do here in this paper, we provide two extensions. So one of them is for the drifting case. So here we will assume, or we will not assume, that there is a fixed weight vector that performs well on the data, but maybe the function drifts. So maybe the definition of what a spam is changed over time. The other extension is selective sampling. So instead of viewing or receiving the labels of the entire inputs all the time, we will allow the algorithm to choose on what examples it wants to receive the label. And what we're going to do is we're going to put those extensions together and have a selective sampling algorithm that works in a drifting case. And there is something counterintuitive here, because in selective sampling, we assume that whatever was will be, again, in terms of behavior. Therefore, we don't need all the labels, and we can restrict or refrain from sampling or receiving labels. On the other hand, in drifting case, we assume that things may change over time, and therefore there is a need to constantly receive labels. So we want to somehow balance between those two cases. So let's start with the drifting case. Note that analysis of our bound will be of this form. So this is very similar to what we've seen before. Let me highlight the differences. Here, we are not comparing the performance of the algorithm to a single weight vector, but to a sequence of weight vectors denoted by UT. Before we had only U. But now the regret could be a function of this sequence of U's. So we denote it by V. That will be the total drift or the amount of non-stationarity. V here stands for some sort of variance. And the regret now could be a function of not only the number of examples, but also in terms of this quantity V. Note that when U, T, all of them are the same, we are reduced to the previous setting. And here we will have a single U, and our RT will not be a function of those differences, but only of T. Our starting point was from a very elegant and nice idea of Forster from 1999 and Azur and Warmuth from 2001. And this is called the last step min-max principle, and they used it for regression. So what we do here is say, okay, how we will derive our algorithm? We will start from the bound and try to find an algorithm that is optimizing the bound. right? This is makes sense. So what we have here, we have the bound or the difference between the performance of the algorithm and the performance of some competitor U. This is for regression, and the squared loss is used. And what we say, okay, assume now that this is the last round. So all the U's, all the Y's are already known, and all the Y hat are already made, except the last one. We now need to make a decision for the last Y, or the last Y hat. Our goal is to minimize this quantity. We want to minimize our loss, and the adversary wants to make things bad for us. So the adversary wants to pick Y such that we will have large loss, but at the same time, the performance of U will not be harmed too much. And so we need to solve this optimization problem in order to make the best min-max, last step min-max prediction. And Forster showed a regret of log t for regression. What we do, we take the same intuitive and nice idea, and we extend it both for classification and for drifting. So let me go over the differences between what we just saw and what we have here now. First, instead of having a single U, now we have a sequence of U that we need to solve here, both in terms of the minimization here and in the loss. This is because we want to work in the drifting case. We have this additional quantity V here. There are two parameters, B and C, that are trade-offing between the different quantities, the loss of the competitor, the variance, and the norm of the first weight vector. Additionally, since we work for classification, we use a max over where Y could be either -1 or 1, and Y hat could also be -1 and 1. Note that we still have the squared loss. This is because that's the only thing that we know how to solve. So maybe in one of future work, we would like to replace the squared loss with a hinge loss. Note that if you allow those Y and Y hat to be reals, then we get to a case where we have non-stationarity regression, and we presented that in AI Stats last year. And also, when C goes to infinity, V here must be 0, because we want to minimize over it, and then we get the stationary case. So we put a lot of effort to solve this complex min-max optimization problem, and here is the solution. And I want to highlight a few properties. First, this is a linear predictor. The Y hat is a sign of the inner product between X and some vector, and this vector is essentially a product between some matrix and another vector. This matrix we change its eigenvalues in two ways. First, because of this operation, we shrink a bit the eigenvalues, and then we increase them with X. So if you think about D as intuitively like the second moment of the data, we shrink about a bit the second moment of the history, and we add the new example. And this makes sense because we work in the drifting setting. We want to forget what was before. We also update E, and it gets an additive update. We add to E, we multiply it by some matrix and add YX. Note that when C goes to infinity, we get the second order perceptron of Niccolo Cesabianchi and his colleagues. And we also would have that this matrix will be the identity. So E we just get an update similar to the perceptron algorithm, but there is some whitening matrix which is related to the accumulative second moment. If we put everything together, we get the first algorithm of the paper. Let me go over some of the details. We initialize the algorithm to be D0, this matrix, to be the identity matrix times some constant. I remind you we have two parameters, B and C. C relates to the variance, and B relates to the norm of U. E is initialized to the 0 vector, and K is the index of number of mistakes. This algorithm, and all the algorithms that I will show today are mistake-driven, so we update only when we make mistakes. So there are two indices, T for the time, and K to the number of mistakes that we have until now. Given a new input X, we pretend or we modify the weight vector using that X and compute the margin and make a prediction. And now we receive the label, and if indeed there was a mistake, then we keep this candidate a matrix D, we update E, as we saw before, and we increase our counter. So that's the first contribution. Let me go now and tell you how we modified that for selective sampling. So what's the difference between selective sampling and online learning? Here, we are not getting the label Y all the time, but the algorithm needs to decide if it wants to receive the label, and only if it receives the label, it can make an update. Nevertheless, we count mistakes for all examples, even for examples for which we didn't see the label. So the analysis and the performance of the algorithm are related to the entire sequence of input, even though the algorithm itself is not aware or there is lack of information in terms of the label Y. So let's see some illustration. Let's say that I have two labeled examples, a red and a green, and I have some hyperplane. Now I see a point, and I need to decide if I want to query its label. It's a one-time shot. If I query the label, then I will get the label. But if I will not query the label, I cannot get back to the example again. So this is one difference from selective sampling and active learning. In active learning, we can go back to examples that you've seen before and say, well, in retrospect, I would like to get the label of that example. But here in selective sampling, once I decide not to query the label, I cannot go back and ask for the label of that example. So here we say, well, it's a bit far from the hyperplane, so probably we are correct, so we are not querying the label. The same for here, the same here. And now there is an example that is pretty close to the hyperplane, so we say, okay, let's query the label. Well, it was a good decision because we have a mistake. So now we can update using, let's say, the perceptron update or some other update. And we proceed, we get another example and another example. We say, well, this is close, so maybe we should ask. And we query, and we see that now we were correct, and we don't make any updates. What we do, we modify the algorithm that I presented before. We call it LASER for last step algorithm for classification. And now we add a selective sampling. So here, after we make a prediction, we need to decide if we want to query or not to query. And what we do, we use the quantity of p hat, this margin, and say, well, if p hat in absolute value is large, namely we are far from the hyperplane, we do not like to query. But if p hat is close, and its minimal value could be 0 in absolute value, then we must query. And we use a stochastic decision. So we toss a coin, and we call it ZT with probability, a Bernoulli distribution of some parameter A over this sum. And if and only if z is 1, then we query and we proceed. So we perform update under two conditions. First, we queried, and second, there was a mistake. Otherwise, we do not update. Note that if p hat is 0, then we have a over a, and the probability of querying is 1. And if p hat goes to infinity, or it's very large, then the denominator is very large, and the probability will go to 0. And what we call large or small, that's essentially the parameter A. So this is the algorithm, or how we modified the algorithm that we had for the drifting case to selective sampling. So to put things in context, this is the algorithm that I just presented. If the parameter A goes to infinity, we sample with probability 1, we query with probability 1, and we get the algorithm that I showed you before. If C goes to infinity, but A is finite, we get a selective sampling algorithm based on the second-order perceptron that was presented by Niccolo Cesabianchi and his colleagues. And if both goes to 0, we get the standard second-order perceptron that was presented by in another paper by Niccolo Cesabianchi and his colleagues. I want to tell you a bit about the analysis. Clearly, there is no time to go into details. What we did, we used a unified analysis. So we built or proved some lemmas that were good for both settings, both selective sampling and full information, and then we made different decisions at some point. So let me start with a regret bound or mistake bound for the full information case. And what we have here is that we bound the sum the number of mistakes with two terms. The left term here is the loss of the competitor. We've seen that before in the general case. Then we have, this is essentially the regret. How much do we lose because our algorithm is online and is not observing the data beforehand? Let me add some comments. So we have here the square root, the norm of u, the variance, and this quantity. Note that if we want the bound to be small, we need u to be in some sense orthogonal to x. But in the same time, u cannot be orthogonal to x because the hinge loss will be large. So there is some trade-off here between these two quantities. And there is multiplied by this quantity. I will get to that quantity in a second. When v goes to 0 and c goes to infinity, we recover the second-order perceptron bound. So we're not only recovering the algorithm, but we recover the bound, the same bound that was proven by Niccolo Cesabianchi. And also, if we choose the optimal value of c here, one can see that the regret behaves like t to the 1/3 multiplied by the variance to the 2/3. So as long as the variance is not linear in t, we get a sublinear regret, which is a desired property of an online algorithm. About this quantity, we can show or we can bound it by a sum of two things that essentially are 1/c times some constant. Therefore, there is some non-trivial value of c that optimizes the bound, because here c is multiplying the quantities, and here we are multiplying them by 1/c. That's the first bound. For the second bound, we have this relation. First, note that since the algorithm is stochastic, all of our quantities are expectations over the decisions of the algorithm. So we bound the expected number of mistakes the algorithm makes with respect to the internal randomization of the algorithm. And as before, we have this quantity, but now note that we have here z. So we're not only comparing the performance of the algorithm to the use, but only to where there was a query and where a mistake was made. So this quantity could be lower compared to the case where we always queried, because there would be just less terms here in the sum. The second thing is the same thing holds for the variance. So now we compare the difference between consecutive use, but only consecutive use which were queried and a mistake was made upon. Again, we have here expectation. We saw that term before, and the same here. Everything is with expectation. Note that when a goes to infinity, we recover the algorithm that we mentioned before, yet the bound goes to infinity, right? Because we multiply here by a. So in this sense, this analysis is a bit weak because it cannot recover the other analysis, and essentially we need two theorems and not one. And this is, we believe, some artifact of the proof technique that we used. Additionally, we can optimize a, because again, here, because of this term, we want to maximize a, and because of this term, we want to, here we want to minimize, and here we want to maximize a. So there could be some optimal value of a which will minimize the bound. Why did I write here theoretically? Because if I modify a, I modify the behavior of the algorithm, and therefore the right-hand side will also be, modified. I don't have time for all the simulations and experiments, so let me briefly go over 2 or 3 of them. So the first, here we use synthetic data set. Okay, so we have a random vectors in dimension 50. In every 500 iteration, we change the weight vector. That's why you see those peaks here. And we compared 6 algorithms all together. The first, the good old perceptron algorithm, the second-order perceptron algorithm, 3 modification of the perceptron for data with a shift or drift. One of them is called the shifting perceptron, in which every time before we update it, we multiply it by some number less than 1. So we always shrink it towards 0 to forget the past because there is some drift. In run 500 is that from time to time we forget example. We are not allowing ourselves or the algorithm to remember more than 500 examples in our algorithm. Okay, so as you can see, I will skip some of the observations that we have here, but this algorithm works the best compared to all other algorithms. The x-axis is time, or number of examples, and the y-axis is accuracy. So here, higher is better. Here we have results of what we call real-world data. It's a USPS data, and it's a multi-class OCR. We need to recognize digits. So every 500 iteration, we split the labels into two different sets of positive and negative. This is how we reduced multi-class to binary. And again, the trend remains the same. In the sense as the algorithm that we presented, LASEC performs the best. The gap from the second order perceptron is pretty small, but still exists. Let me move now to the selective sampling results, and I'll finish in 2 slides. So what we have here, we tuned all the algorithms that we compared such that the query rate will be about 10%. So even though there are 10,000 examples, we saw about only 1,000 labels. And each algorithm chose which labels it wants to observe. 5 algorithms were compared here: the selective sampling perceptron and selective sampling second order perceptron. An algorithm called BBQ is due to Francesco Rabona, Claudio Gentile, and Niccolo Cesabianchi. And this algorithm, whatever it queries, it updates. Therefore, we also added a different variant in which we update only when there is a mistake. And you can see that first, performance is not very good because only 10% of the data observed. And some algorithms perform very well in the beginning before there is drift, but then at some point their performance becomes bad. And this is because they stop querying. So those algorithms are querying in the beginning. Then at some point they make a decision or conclusion that everything is okay, and they stop querying, and then the performance gets bad. We see a similar trend here. Here we query for 40% of the data. And let me just skip to the some related work. You know what? If you want to see this table, come to the poster. And let me summarize. So I showed you an online learning algorithm that is based on the last step minimax ID for drift and selective sampling. We have a mistake-bound analysis and some simulations. If you want to see more, please come to the poster 118. And next to that poster, there's another poster, 117, in which we take those ideas and use or lift them up, where we use aggressive updates, which improve performance very much. Thank you very much for your time.
One quick question. So this A parameter for updating, how do you set that? Do you have heuristics? Do you have an interpretation, like in some sort of like Bayesian context, how you can interpret that parameter, how the updates work?
So we have some heuristics to choose it, but in those experiments or simulations, what we did, we just play with it a bit for a short intervals to see what values we need to choose to get some specific querying rate, because if you want to compare algorithms, you need to know you need that they will have about the same query rate. So we played with it a bit such that we will get equal query rate or close to equal.
Okay. Well, thanks Koby.